Welcome to the second talk. Payam Bayreni will teach us more about Bayesian statistics.
Hi everybody. We're going to talk a little bit about Bayesian statistics. I try to not to go deep into the math and try to go example by example from discrete case to continuous case to a little example on inference and how you may sometimes prefer at least trying the Bayesian versus frequentist, and sometimes you may get a little bit of advantage in doing so. So a little bit of history. Although the name is Bayesian and is kind of references from space, later on Richard Christed actually published this theory, and later on Laplace actually worked on it and extended the Bayesian interpretation of probability. So a really high-level overview is that on a frequentist approach, what we do is we sample from population, we look at samples, and try to do an inference from our sample statistics to population parameters, right? And in this mindset, the only source of error is just our sampling error. So, and we say, okay, sample more and more and more to get closer to the population statistics, right? But in Bayesian approach, we acknowledge that all of us have beliefs, biases. We know about the thing that we are measuring. So we use that belief and use that what we know into our inference or our statistic type of calculation and use the evidence that we are gathering together to get to the point that we have some posterior beliefs about the population. And the nice thing about the Bayesian approach is that different people can start from different beliefs, different universes, and the more data, the more evidence they gather, they actually converge to the same truth about the population. So it doesn't matter if you think that the previous belief is that everything is uniform and every value is possible, or you believe certain values are more likely than the others. Ultimately, given the evidence, everybody converges to the same belief about the universe. So let's start with this example. You go to a movie theater and somebody drops their ticket. You just can see them from back, right? So you see they have long hairs. And intuitively, you may want to say, ma'am, you dropped your ticket, but also it's likely that it's actually a guy, so you may want to say, excuse me, sir, you dropped your ticket. And we want to know which one is kind of more likely. And what if the same thing happens in the line of men's room? So then your belief changes and your conclusion may change. So we actually look at this example in more detail. In general, let's say that for women, it's kind of 50-50 between long hair and short hair. And for men, it's maybe 5 to 95, meaning five people have long hair versus 95% have shorter hair. Population, right? So what happened in the hallway, we can assume the hallways is just kind of what happens in the general population. So you can have still the same probabilities, but and you see that because looking at this chart, you see that it's 10 times more likely that who you are seeing is actually a woman. So intuitively, you want to say, man, you dropped your ticket, right? It may be wrong, but when you're in the line of the men's room, so you may, out of like 100 people in the line, there may be 2 ladies just talking to their partners and still standing in the line. So you may have like 2 people in the line and 98 people are men. So here the distribution is different, right? Still the same distribution as the general population. Out of those 2 ladies, one has, let's say one has long hair, one has short hair, and for men is 5 to 93. So here, because we are in that situation, men are 5 times more likely to be in that line. So we use our belief to say, okay, Sarah, you dropped your ticket, right?
Is it a belief or just context?
Yeah, context is a belief. In the frequentist approach, you don't use any context. You just look at what your evidence is, right? So any context, any belief, anything that you know about that, the data you're gathering in the Bayesian approach can be used along with your evidence to push you towards a conclusion. So let's work a little bit of math here. So in the hallway, we have, as we said, 50-50 men and women. And in the line of men's room, we have 98% men versus 2% women. These are called our prior belief in Bayesian terminology. So before we gather any data, we have this belief, and then we gather data, and then we calculate the probabilities afterwards. So the conditional probabilities, meaning what is the likelihood that we are having a line curve given, it's a woman is 50%, and for men is 5%. It's still the likelihood. So given, as we saw in both situations, this holds. We have 50% of men, 50% of women having long hair and 5% of men. And then we introduce a concept called joint probabilities, which is the probability of A and B, right? That's P of one with long hair, and so when we want to use a joint probability, we want to have both conditions true. So we can say, what is the likelihood that's a woman? That's 50% in a general situation. And what's the long hair given? We know that that's a woman. That's also 50%. So we end up with 25%. And we can calculate all these different scenarios in the general hallway situation. So the joint probability of woman with long hair and short hair are 25%. And man with short hair is 47.5, and man with long hair is 2.5%. So still the conditional probabilities are the same, but this time with a different prior in the men's room, in the line for the men's room, and now we see that given we start with a different prior. In the joint probabilities, we have woman with long hair is 1%, and man with long hair is 4.9%. So here, because we started with different priors, after updating, we get these results that is kind of like 5 times more likely that you're talking to a man. Any questions so far?
Actually, since we already know it's long hair or short hair,
Yeah,
you
yeah.
may want to say if it's long hair, then this person is a man, this
Yeah, yeah.
person is a woman, and total is 100% for each case individually.
Yeah, yeah, that's true. So this is what we mean here, right? So I haven't actually put the other cases here in the conditional probabilities, but since if we know it's a woman, we have long hair 50% and short hair 50%, and if we know that's a man, but the thing is, we have a different type of conditional probabilities when we are trying to ask, right? What we are trying to know is what is the probability of being a man or a woman given that we know is a long hair, right? So that's the whole thing that Bayesian formula is trying to do, just reversing the sides, starting with one of them that we know and going to conclude with the other that we don't know. And lastly, the last one is marginal probabilities, which is all the cases that some sort of evidence can happen. Right, for example, for what's the probability of long hair in general? So that long hair should either come from a woman or from a man. So we can, because it's an or, we can sum the results together, and we end up with 5.9% for the case of men's line in the men's room.
Okay, yeah, that's what I was going to ask. So these are all probabilities in the context of
yeah, in the context of men's room, these are the probabilities of someone having a long hair.
And that's not a condition on the ability.
No,
it's not
it's
conditioned.
pretty general. And we are using all these components in the formula to come up with the condition, the other condition that we don't know. So, and again, the probability of having a short hair is either you're a woman with short hair, man with short hair, and stats like just 94.1 in that context.
It would have to add up to 1 over here because those are the only two possible.
Yeah, because we don't have any other option, right? It's either short hair or long hair in our imaginary universe. We don't have like middle hair or something. So, what we don't know is probability of man given a long hair, right? This is what we want to calculate. We already know the probability of man with long hair, which is the same thing as saying the probability of long hair and the man, right? So because these two things are basically the same and interchangeable, we can just move it around, and these are giving us two different results. We can just put these two equal and end up with the formula for Bayes' theorem, which is if you want to know the conditional probability of A given B, it's the same thing as conditional probability of B given A times probability of A divided by the marginal probability of B. So when you're looking at, okay, I have this prior, I know this thing about A, which is PA, right? And I already know the likelihood that if A is true, what is the probability that B is true, right? And marginal probability is just the general case that all the different cases that B can occur. So what we are looking for is a specific case, and what we have as marginal probability is the general case. All the different cases that long hair can happen. We are looking for men given the long hair, but in the marginal one, we have all the different cases. So men given long hair or woman given long hair. Okay, so if you're looking at the hallway case, we have this formula of woman given long hair using that formula we just saw is the reverse long hair given woman times P woman divided by P long hair, which is 96%, but in the case of men's room, it's just 17%. So this is just doing the math of what we already kind of intuitively know, right? In a general case, we would kind of guess that that would be a woman, and in a specific case, we would kind of guess that is more likely to be a man, right? Any questions so far? We are good with the definition and the formula and everything. So this was this was like the discrete case. We have like different options, and different options have like very set priorities, and we have like 2 cases, 3 cases, a couple like countable cases that we can calculate the probabilities for, and we can go ahead and do that.
I guess this being probabilities, you take a risk. Yeah. So it's better not.
There you have like a 4% risk of that in the hallway you're actually calling a ma'am.
So maybe it's better to say excuse me.
Yeah, you can do that. But we try to at least get closer to the truth. You can always say I don't know, and you go along with it. So the cool thing about the Bayes theorem is that it still applies exactly the same with the case of probability distribution, which is basically saying that my range of values are continuous, and each value has its own probability. Specifically, they are 0, but in the range they have some values being the area below the curve. And this is why it was not easy to use this theorem before computers, because it's getting really hard to integrate over some random curve without the computer, right? So, but now that we have all this processing power as discussed in the previous presentation, let's use this theorem to have like a kind of better judgment and better inference, that sort of thing. So let's look at an example. So let's say I have a dog and I bring that dog to a vet clinic and they weigh that dog. But because it's like a small one, it's restless, it jumps a lot, moves a lot, every time you weigh that, it's just different, very different values. Like 14.1 all the way to 17.5. And we want to have a close to truth value for the actual weight, because we are deciding the food intake and etc., given that number. So if we just use our regular statistics, what we learned in school and everything, we have 3 values, so we can calculate mean, calculate standard deviation, calculate standard error of the mean, and we end up having a chart like this about the weight of my dog. Right? So these are 3 measurements. One of them is pretty all the way to the right, and the other ones are lower than even the sample mean that we just got. And we are trying to say, okay, how we know what's the actual value? Should it take more food, less food? What should I do? And this chart with these 3 values doesn't give that much of a opinion or idea about what we can say about the weight. Let's see how we can kind of fix that. Still, we are saying, like, given all these measurements, my posterior probability is the probability of weight given all these measurements is equal to the prior of each of these values of the weights, which is going to be a probability distribution, and the likelihood that this measurement happens given that probability distribution or prior distribution. And my marginal likelihood. So here we can
this part,
show.
prior. What does it represent? The prior part?
The prior is your belief about, even before measuring anything, what do you believe how each of those values of weight are likely. So we end up actually having a curve called probability distribution, saying like, I feel like this value is more likely, this value is less likely, and this should be in this area, that sort of thing. And if you don't know anything in the Bayesian paradigm, you can still say, as you said, I don't know, this is the low risk option, just go with, I have no idea. Everything is equally likely in uniform distribution from negative infinity to positive infinity, right?
The probability of a negative weighting should probably be zero.
Yeah. In this case, I'm talking generally. But here, yeah, you can say from 0 to positive infinity, everything is equally likely. And you know that given your size of the dog, there should be a limit. So probably like 20 or 25 pounds is just a limit. But still, you say from 0 to that point, everything is equally likely. And if you do that, given those measurements, we still end up with the same chart. Because when you look at the formula, this one is constant because marginal likelihood is an area below the curve for that uniform distribution. This one is constant because every value has a probability. So this, basically you start with this and you put it times a constant value. And you get this, get the same chart. Which is a good thing. So you can say, if you're pretty conservative, you can still use Bayesian approach, but start with nothing specific. And you get the same results as the frequentist approach. But you can start with something a little bit more, something that makes more sense. Saying that the last time I came to this clinic, the weight was 14.2. I don't really notice holding that dog anything different, and probably it's like plus minus half a pound or something. So we can start with something like this as our prior, saying like 14.2 as the median, as the mean, and the standard deviation is 0.5 pounds. So you can use that as our prior and then see how it's getting updated using the evidence we gather. Interestingly enough, is when you apply this formula on your prior belief, which is here in the black line, we end up with the posterior belief, which is in orange. So you see that because this one was way off, given our priors, it had kind of no value, kind of ignored. And these two, which are in this area, push this chart a little bit toward 14 and a little bit higher in the middle. And this would give us a better idea if you want to say anything about the weight, if we use this chart compared to what we have with the frequentist approach, we can have something closer to the truth. And also closer to our prior belief. So both of them are actually contributing to the results. This is the result for the frequentist approach, where we end up having like 15.2 and 1.5 standard deviation, and this is our result for the Bayesian approach. Any questions so far?
How much does the dog weigh?
At least here we can say it's highly likely that is somewhere between 15 and 13, and no way is actually weighting 17, which in this scenario we have some probability here. It's not 0. It's pretty likely. It's pretty likely to have like 16. It's pretty likely to have 15. But after we update our prior using the evidence, these are all out. There is no way that our dog is weighting 16.
But how much does he weigh?
We at least can say like somewhere in this area. It's all about saying like the more I gather data, the closer I can get to the truth, right? So it's just 3 evidence, 3 measurements. I can be pretty sure that this is the area that my dog weighs now. And if you go by like median or mode of that distribution, you can say something like, I believe this dog weighs this much plus minus that, because it's also a normal distribution.
Can you show the formula that got this curve again at the posterior and prior? Oh yes.
The point is you need to calculate this formula again and again for each of those evidence points, and then put them together as a final curve.
Yeah, but I understand the multiplication, but what's the marginal likelihood?
Marginal likelihood is the likelihood of each of those measurements.
But
How they can happen, given the different scenarios, like the long curve we have. So how long layer is likely, given you may have a long layer with a woman and long layer with a man. So you actually integrate over all the different scenarios that measurement happens.
yeah, but that's the same as prior then. What's the difference? I can't distinguish between prior and
So prior is
marginal.
what you believe about what you're measuring before you actually measure, right? And the marginal likelihood is what you believe about how each of those evidence is likely. These are totally different things, right? So you know the prior before actually measuring, but you cannot calculate the marginal likelihood because we don't know the evidence yet. You need to have the evidence first and then go through the evidence.
Basically, that's a long
how
day.
each of, yeah.
That's a long.
How each of them is likely. I'm sorry.
So do you typically not calculate the marginal when you're doing this?
You do.
You leave it out as a constant, or you?
No, but initially it was left out as a constant because the whole thing was, I mean, if you want to get to the final plot, you need to actually have that value, which is the integrate. But we just wanted to, just wanted to explain that why is it that if you're starting with a uniform distribution, why the shape of the curve is exactly the same before and after. The height might be different, but it's not moved around or it's not condensed around some value if you're starting with a uniform distribution. But if you know something, like you say, okay, my prior is that the weight is a normal distribution around this value, that's going to be both moving the curve and also changing the shape of the curve towards some specific value. Okay. So as we saw in both situations, the prior has a major effect on the result. So we need to kind of be careful about what we say our prior belief is, and be careful about like how we express it. But as we discussed before, even if you have kind of a prior that is very off the truth, it can converge to the actual value with enough evidence. The point is, what you kind of mentally think as impossible may be probable, So you may need to assign non-zero probabilities beforehand to that impossible cases and give them the chance to grow and update with evidence. So if you assign non-zero values to those cases, no worries, it's going to converge with enough evidence to the actual values, because the more and more you have evidence around those specific values, it shows that those are the actual values, and it's going to shift the curve toward those values. Any questions?
So if something is actually assigned a zero probability, the curve will never shift to it? Is that true?
No, yeah, that's correct. Yeah, if you start with something that you say there's no way that's going to happen and it's absolute zero, no matter how big a likelihood gets times that prior, it's just a still
Goes to zero.
right?
So is it unwise? So in our dog example, you still shouldn't assign a zero probability to negative weight?
Yeah, that's a good thing. Exactly, that's a good thing. That's like, so
physics.
even all, yeah, all you know about everything that you're measuring can be actually incorporated into your measurements. So you can say, if I'm like measuring the weight or measuring the age, that's a non-zero value. Age, most of the time, is not more than like 100, right? Anything that you know about your population can be incorporated as the belief into all your measurements and can quickly converge to the actual truth about your population, as opposed to saying like, okay, this is a normal distribution with this value, and everything is likely all the way to positive infinity and negative infinity, which is not the case usually. Everything that we know, what we know about temperature, what we know about like anything physical, all the physical events, everything. So all these can be incorporated into our calculations and used to update towards our posterior belief about the universe. Any other questions?
What if a person with long hair comes to weigh the dog?
We can mix and match all the discrete and continuous probabilities and see what happens. It would be an interesting problem to.
But no, seriously, they can be correlated. I mean, these scenarios, can you have a situation of correlation of phenomena, you know, or the phenomena have to be independent, yeah?
Yeah, the good thing is you can start with the prior and then say, okay, given this prior, which is in our case, which may be like a discrete probability, and this happens. Let's see it happen, and then given that it happened, what is the likelihood is this other continuous event, right? So you can actually, the nice thing about Bayesian approach is that you can chain all these. Either like different events to each other, or another one is that you don't need to have all the evidence at the same time. You can gather evidence as you go. So you can start, okay, this is my prior and this is my first evidence. Okay, the posterior is this, and then use that posterior as the new prior, and then look at the next evidence, and then update as you go. So that way you can also kind of like use event processing to update your prior probabilities as they happen. It's nice that these two kind of are related. So let's discuss the inference problem. So somebody has assigned us to look at the M&Ms, and our job is to say what's the proportion of yellow M&Ms in a batch, right? What we know beforehand is either 10% or 20%, and we need to sample and decide. And sample calculation is costly, like let's say M&Ms are really expensive, we cannot buy a lot of M&Ms, and that sort of things. So we need to be careful about sampling, we need to care about like all these things, and then see what we end up given different approaches of inference. If you're using a frequentist approach, as we know, we usually start with the null hypothesis, saying like, okay, my null hypothesis is that 10% are yellow, and my alternative is that more than 10%, because I don't have any other means of saying 20%. I would say, okay, alternative is more than 10% are yellow, right? The regular significance level is 5%, and I have a sample of 5, and one of them is yellow. This is my evidence. So the test is if the observed or more extreme happens, what's the probability that observed or more extreme happens in the direction of alternative, given the null is true. So we want to know what's the probability of me having one or more yellow M&Ms in a sample of 5, given that the probability of yellows are 10%. And if we calculate that, we end up with 41%, or 0.41. And 0.41, as we know, is not small enough, so we fail to reject the null. And we conclude that there was no evidence for me to reject the null that the proportion is 10%. Although, from that sample, we already know that the proportion was 20%. But because of the sample size and because of other problems with this specific issue, we couldn't reject the null. And the nice thing about this is if you go to like sample size of like 10 and 15 and 20, it's still the same, doesn't matter. So in frequentist approach, we fail to reject the null because our p-value is not small. But what happens in Bayesian approach? One of other advantages of Bayesian approach is that we can concurrently, simultaneously check different hypotheses at the same time, rather than picking one thing and say, this is true and this is not true. We can say hypothesis 1, 2, 3, 4, 5, and run the formula all at the same time, and then look at the posterior probabilities and say which one is actually more likely, right? So here we start with two hypotheses, 10% and 20%, and with priors of, so our prior belief, we don't have any bias towards any of these hypotheses. We're saying it's like 50-50 likely. And again, observation, one yellow out of sample size of 5. And our likelihood, when we calculate it, is that likelihood of one yellow given this hypothesis 1 is 33%, and given hypothesis 2 is 41%. So here, using Bayesian approach, we actually have the 41%, and then we start calculating the posterior. The probability of hypothesis 1 given data is 44.6, and probability of hypothesis 2 given data is 55.4. So here, the chance that hypothesis 2 is true given our data is way more than hypothesis 1. So we end up actually accepting hypothesis 2, which we didn't in the frequentist approach. In frequentist approach, we couldn't reject hypothesis 1, which is 10% yellow, and we said, okay, I cannot reject, so I have to accept hypothesis 1, 10%. But in Bayesian, so these two approaches can actually end up having two different results, and we need to make sure that we know why and how we are using each of them, especially in the inference case.
I have a question here. is it just maybe more conservative in the frequentist approach? So in this one, you just accept it because it has a higher than 50 probability? Would maybe
No, given two cases, not just higher than 50. I check both of them and pick the one
or
with higher.
with higher.
Okay.
But what if you wanted one? What if you were strict and you said you would only accept one if it was, say, twice as big as the other probability, or
But you see, like
I guess you just have two different levels of evidence, and then this way you would pick one or the other. There's no third option, which in the frequentist you sort of pick neither. You fail to reject the null hypothesis, but you don't. That doesn't imply.
If we fail to reject the null, we usually just say null is true, and we don't say null is true. We say given the evidence, we cannot reject the null, right? Which is kind of implicitly accepting the null, right? And so here,
I mean, here, if you constructed a rule, something like accept, or you would have a strong enough belief if your hypothesis had a greater than 95% posterior, then neither of these would meet that criteria.
but the thing is, in general, when we are trying to weigh different options, we just go by their probabilities, right?
Yeah.
So let's say this one is not 95%, but that one is. And I understand that these are not actually like systematically, we are not talking about the same thing. These are two different approaches with two different mindsets and everything, right? But I'm just focusing on the result right now and saying that if this guy uses this approach all the way to the result in a black box, and the other one uses this approach all the way to the result, these two don't match. I'm not saying like they should actually get to the same result because they're totally different mindsets.
In practice, wouldn't the goal here be just to determine which of the two is more likely? And so it doesn't matter if it's 55 or, I mean, you wouldn't even have to divide by the marginal if that's true. If you're
That's correct. Yeah.
If you're doing an extra, because they both have the same.
Yeah, marginal for in this case, because we are talking about the same thing, marginal probability is going to be the same thing and doesn't matter. I just wanted to show the full calculation of calculating the posterior and see what would the results be, and then compare the results like H1 versus H2.
But if you
But
frame your
yeah,
problem
you're right. In this case, the marginal doesn't matter.
Unless you wanted to express it as a probability.
Yeah.
Because if you don't divide by the marginal, you don't have a probability and stuff.
You're right. Yeah, you're right. But again, marginal can be easily calculated here. In other cases where we are, as you said, if we care about like which one is greater, we don't need to even go all the way to calculating the marginal because it usually is complex and it's the same across the board. So just for comparison reasons, we don't need to do it. Yeah, that's it. So at the end, we see that the results are still the same no matter the sample size. So if you go like, as I said, 10, 15, 20, 25, they are still the same. And every time the Bayesian one gives higher probabilities to H2. And the tricky part is that frequentist one is sensitive to which one you pick as null. If you have two different options, you pick, okay, my null is option 1, and I say the alternative is not option 1, which means option 2, and you start doing everything. The result would be different if you pick number 2 as your null and not number 2 as your alternative. So in this case, if we start with hypothesis 2 in our frequentist approach and do everything and we fail to reject number 2, so we keep the number 2 as our belief, and everything would be fine. So this is also tricky that, at least in discrete options, it's the frequentist approach is sensitive to what you pick as a null. And you may end up accepting something that doesn't hold because you didn't kind of pick the right one, and you never know beforehand. But it was a nice observation.
Isn't picking a null hypothesis a sort of prior? Like, you might use some prior knowledge about the problem to choose a null?
If you knew, that would be great, but even like as you saw in the Bayesian approach, we started with the prior of 50-50, so we don't know which one is actually even 1% more likely, but we end up with kind of a correct result. But yeah, if you know anything, that would be kind of say, okay, I'm starting with something I believe is a little more likely and see if we can reject it or not. That would be great. But yeah, in real world, probably we don't know beforehand.
In fact, the frequentist approach has a prior baked into it, which is unique, which means if you're looking at going, you assume by default that they're likely. So it's kind of baked into the
And these are a couple of references, like a couple, like the first part came from the Brandon Rohrer presentation, and the second part from the course on Coursera from Duke University on Bayesian course. And Nate Silver's book on the signal and the noise, probably you have heard it, although it doesn't talk specifically on the Bayesian math and approach or anything, the whole thing is about, the whole book is about like why we need to use Bayesian statistics instead or as a complement to frequentist approach, and what other advantages it may have in different scenarios where frequentist approach is not applicable. Thank you.
Thank you. I still want to thank our sponsors, Circle for the Pizza and Atomic for providing the space, and Shopify still for paying for our meetup. Okay, so next week we have a special event on Thursday. So then we have the head of data science of TalkIQ, who is talking about what they are doing here with building their application for the subscribing the sales talks and then doing cool analysis based on NLP and some extra machine learning on top of this. So you're all welcome for this one. Next for May, I have already one volunteer who is talking. And if you are interested to also give a paper talk or something, you can say after the meetup, or otherwise just send me a message on Meetup. Okay, and thank you all for the speakers today and the great presentations.